Okay, so I want to introduce the concept of curvature. And let's start with talking about parametrization. Remember, we talked about parametrizations are different ways to take a curve and describe it with a vector function. Okay, so a parametrization is smooth on an interval if the derivative vector is continuous and the derivative is not equal to 0. Okay, so if the derivative vector is continuous and it is not equal to the 0 vector, then we call that parametrization smooth. And a curve is smooth if it has a smooth parametrization. So smooth curves are things like helixes and stuff like that. Not smooth would be something, or say if you're zigzag or going in, going upstairs in a non-smooth way, if there's a lot of jerk, if you will. So when the tangent vector turns, it does so continuously. So I just want to talk about this just a little bit. What does that mean? So think about the tangent vector, tangent vector. Now this tangent vector is actually constant, right? Which makes sense because this is a line. But now, all of a sudden, the tangent vector changes shape very sharply, if you will. Whereas over here, look up here, we still have tangent vector. The tangent vector is changing, but it's changing gradually. Does that make sense? So no sudden moves. Okay, so that's a way to think about smooth curves versus non-smooth curves. Okay, when we're talking about curvature, our definition only applies to curves that are smooth. Okay, so now recall that we had the unit tangent vector. Okay, and what we did to get that unit tangent vector was essentially take the function that's going to give us the tangent, right, that derivative function, and then scale it by 1 over the magnitude. So we're normalizing that, right? So we're scaling it by this factor, scaling that derivative function by this factor so that the result is a unit vector, number one, but it has the same direction as r prime, so it is tangent. Okay, so remember that formula. That formula allows us to see when our curve is curving, if you will, right? So as that unit vector, that unit tangent vector changes direction, we can look and see. So notice here we've got the tangent vectors, but we've made them all length 1. Okay, very slowly when C is fairly straight, right? So if your curve is pretty straight, then the tangent vector doesn't change direction that quickly. But as you're going around the more you're curving, the more quickly your unit tangent vector changes direction. Now, do you get an idea of when we say more quickly? Think about how much change occurs from, say, this spot. That's not good to use an arrow. But say from here to here, the tangent vector is changing very little. Does that make sense? Overall, you went from here to here. Not that big of a deal. But now, if we were to consider from here, that same amount to, like, say here, it's going to go from looking like that to looking like that. You have a very drastic change. Do you see that? So it has to change more quickly in order to do the curving that the curve needs to do. Okay. So the curvature of C at a given point is a measure of how quickly the curve changes direction at that point. Because that's what determines, that's how you get curve, is you're changing, that tangent line is changing quickly. Okay? Specifically, we define it to be the magnitude of the rate of change of the unit tangent vector. So the rate of change of the unit tangent vector. So we've got our unit tangent vector with respect to arc length. Remember we talked about arc length last time, right? So we use arc length. So do you remember the arc length formula was the integral from a to t of the square root of the magnitude of the derivative. I need to switch this to be something like maybe x. We put that as x, dx, right? Okay, notice we use arc length. Why do we use arc length? So that when we are defining curvature, it is independent of the parametrization, right? So remember, arc length doesn't depend on parametrization, but if you use curvature and you didn't define it on arc length, but you defined it on something else, another quantity, it could be that changing the parametrization would change the curvature. Okay, we don't want that. So this is our formula. So it's the derivative of that unit tangent vector, right, with respect to the arc length function. Okay, so now computing that is kind of difficult. It's easier to compute the curvature if you can express the curvature as a function of t, right? So more difficult is if you have the curvature just as a function of the arc length. But remember, the arc length, and let me erase this. So the arc length, maybe this is, we're going to do x here. This arc length function is a function of t, right? So if you could write t as a composition of functions like this, right? So t, which we know it depends on the arc length, because that's how we're going to be able to do the computation dt ds, right? Is if t has to depend on s. But we're saying actually s depends on little t. So we can use the chain rule, right? These are our differentiation rules. We can use the chain rule to say that dt with respect to little t is equal to the derivative with respect to s times the derivative of s with respect to t. But now remember that our curvature, this letter here is the Greek letter for kappa. So kappa is the magnitude of that dt ds. So if we look at this formula here, so looking at this formula here, first I need to write it smaller. Dt ds over ds dt. We've got dt is equal to dt ds times ds dt. Okay, but remember that our curvature is the absolute value, is the magnitude of this first derivative. So if we just take the magnitude of dt, that should be the magnitude of dt ds times ds dt. But now remember ds dt, this is a scalar valued function. So this derivative is just going to be a scalar. So that'll be ds dt, right? But now this first one is kappa, that's our curvature, and this is ds dt. or the absolute value of that, dt, want the magnitude of that. Okay, so kappa, just divide both sides by ds dt. That's why we need the s prime to not be equal to 0. That's why we need our function to be smooth. Because what is s prime? Remember, do you remember s prime is r prime of t? So we need that to not be equal to 0. So we're going to divide both sides by this absolute value of ds dt. And that gives us that kappa is, so let's go over here. So another way to write kappa is that kappa is, because you see kappa is by itself now, dt over ds dt. So dt, and we need the magnitude of that, divided by ds dt. We need the absolute value of that. Okay? And then, yes, here we go. So, but remember, ds dt, because we use the fundamental theorem of calculus, ds dt is going to be the magnitude of r prime of t. So, kappa of t, and I'm just going to put in double so that we are very clear that we're talking about the magnitude of a vector derivative of a vector value function in the numerator and in the denominator. Okay. So this is our formula 9. This is for the curvature. All right. So let us put this in practice with an example. We're going to show that the curvature of a circle of radius a is 1 over a. So our goal is to show that kappa is 1 over a. Okay. Now, when you think about a circle, you should think about, so if we have a circle and we may as well put the circle centered at the origin, right? Because the curvature isn't going to change based on the location. Do you get what I'm saying? So if we had that circle out here, it'll have the same curvature as if it's centered at the origin. So let's just center it at the origin for ease of calculation, right? And now we expect the curvature to be constant. It shouldn't matter where you are. It shouldn't matter what your value of t is. The curvature should be constant because those tangent vectors are constant. Does that make sense? Okay, so now how are we going to parameterize? We are told that it is a circle of radius a. So that would be like a comma 0, 0 comma a, 0 comma or negative a comma 0, and 0 comma negative a. The way to parameterize that is r of t equals a cosine t, a sine t. So this is our r of t. And now what about t of t? Now remember, that should be a vector. Okay, so t of t is going to be, we need the derivative vector over the length of the derivative vector. Okay, and that's just, we're just taking that derivative vector and scaling it by 1 over the magnitude. So in order to do this, if this is our r of t, let's compute the r prime of t. So r prime of t, remember you're just going to take the derivative in each component. So that'll be minus a sine t for my first component. And the derivative of sine t is going to be cosine of t. Because remember, a is just a constant. So I have a cosine t. Okay, so I'm going to take this and put it right here. So that's my numerator, is this vector a sine minus a sine t, comma a cosine t. And now what am I dividing by? I'm dividing by a scalar that is going to be the magnitude of the derivative. Okay, so now what is the magnitude of that derivative vector? And I need the square root of the first one squared, a sine t squared, plus the second one squared, the second component squared. And that's just going to be the square root of a sine squared t plus, sorry, a squared sine squared t plus a squared cosine squared t. Are you with me here? And that is just going to be a, because the sine squared t and the cosine squared t are equal to 1. So I can factor out like that, right? And then sine squared t plus cosine squared t is equal to 1. So just get square root of a squared times 1. But that's just square root of a squared, which will be a. So on the bottom here, we've got a. Now, remember, if we are dividing by a, that means that our first component is going to be just negative a sine t over a, and our second component is going to be a cosine t over a. Does that make sense? Okay, so then here we'll have just negative sine t, and here we'll have cosine t. Okay, so we figured out a formula for our unit tangent vector that doesn't depend on the arc length, it just depends on sine t, cosine t. Now in this case, arc length would be the length of the part of that circle. Okay, so we'll say, so our unit tangent vector is negative sine t, comma, cosine t. Okay, now kappa is the, so that is a vector, that is a vector, so I need, so the magnitude of the derivative. All right, so let's do the derivative here. I'm just going to take the derivative of each component. Negative sine t is going to be negative cosine t. The derivative of cosine t is going to be negative sine t. Okay, and I need the magnitude of that derivative. And what do we get? So notice that, let me say this. So t, this is the unit tangent vector, right? So this is, you can think of it as the derivative of a derivative. So we're in the area of second derivative, right? And in terms of vectors, and the derivative of position is velocity, and the second derivative is acceleration. Well, that's what we're looking at. Is we're looking at a ratio, kind of like the numerator is a second derivative, and the denominator is a first derivative. Okay. So this t prime is a derivative of a derivative. Okay, so this is going to be the square root of negative cosine t squared plus negative sine t squared, and that is just going to be 1. All right, now what about this? So the numerator is 1. Okay, what about r prime? Didn't we find? We already found that the magnitude of the derivative is going to be a. So a. So indeed, kappa is equal to 1 over a. Okay. Yeah, so we did that already. Okay, and the result of example A shows in accordance with our intuition. So now remember, we're saying kappa is 1 over a. So if you have a small circle, that means that a is small. So 1 over a is going to be big, right? Because the reciprocal of a small number is a large number. So the kappa is big. The curvature is big. And geometrically speaking, what we're saying is that if you have a small circle, then the tangents have to turn a lot faster, right? The tangents have to turn a lot faster than they would with a large circle, right? Compared to a large circle, those tangents get to turn very, very slowly, right? Okay, we can see directly from the definition of curvature that the curvature of a straight line is always 0. So curvature is the unit tangent vector, take its derivative, but the unit tangent vector is going to be constant, so its derivative is going to be just the 0 vector. So that numerator is always going to be equal to 0 because the tangent vector is constant, right? Because it's a line. Are y'all with me there? So say if you have a line and it's r of t equals r naught, right, plus t times a. R prime of t is going to be a, yes? And so then that's a constant. So your unit constant, unit tangent is just going to be a over the magnitude of a. This is still a constant. It has nothing to do with t. So its derivative is going to be 0. Does that make sense? Okay.